All right, so it's a pleasure today to start the first Quiver meeting of the year with Palash Singh, who will tell us about, who will tell us how to simplify the type A Argyres-Douglas landscape. Take it away.
Thank you, Julius, for the nice introduction and for giving me the chance to talk in your esteemed Quiver meetings. Yeah, this is some work I've done with Chris, my default supervisor, Mario from King's, Matteo, again, a postdoc at Oxford, and Jake, a student at King's. We have done this over the last couple of years, and yeah, the title, if you already know this field, the title should be sort of understandable. If you don't, well, that's going to be my job to explain the title to you. But let me start with some motivation. As with most things in my life, the motivation is SCFTs with 8 supercharges. These are really nice because, again, they're a very good playground for understanding some non-perturbative physics. You can test a lot of non-trivial dualities in this context. In particular, I'm restricting myself to 4 dimensions for the setup. And so I'm working with 4 equal to 2 superconformal field theories, and sort of any excursion in the landscape of 4 equal to 2 field theories lands you most likely in the world of non-Lagrangian 4 equal to 2 SCFTs. Again, them being non-Lagrangian is very interesting because you really have to look for non-perturbative methods of understanding what's going on there. And a particularly important class of non-Lagrangian 4 equal to 2 SCFTs are known as Argyres-Douglas theories. What are these? They have a very loose characterization. Any 4 equal to 2 SCFT that has fractional Coulomb branch scaling dimensions are called as Argyres-Douglas theories. Just to recall, Coulomb branch scaling dimensions label the Coulomb branch moduli space of vacua of any 4 equal to 2 field theories, which in the context of gauge theories is just labeled by giving wefs to the scalars in your vector multiplet. And the fact that these are fractional necessarily tells you that you cannot have an n equal to 2 Lagrangian description for these theories. So they're sort of intrinsically non-Lagrangian. Where do we find them? There are many ways. The first way where they were found, which is by Argyres and Douglas, was at sort of special points on the Coulomb branch of certain Souchy gauge theories. They found that under sort of at a particular point, the low energy effective field theory is an interacting SCFT, which has where some operators have fractional scaling dimensions. That was the old way of getting them. The sort of the more modern stringy type methods to obtain these theories are sort of twofold. One of them is by considering type 2B string theory on some singular Calabi-Yau threefolds in a process called as geometric engineering, where the exact structure of the singularity ensures that your 4D SCFT has fractional Coulomb scaling dimensions. And so you can construct a lot of Argyres-Douglas theories this way. And the other method, which will be the focus of this talk, for me is the classes-like construction, where you consider 62,0 theories and compactify them on certain Riemann surfaces with some boundary conditions for various fields involved. A mathematical object called the Hitchin system makes a big appearance, which I will talk about in some amount of detail here. So yeah, you see them in a lot of ways. One sort of tangent orthogonal motivation to study these is from the mathematical perspective. The associated VOAs for these theories, since these are 4 equal to 2 theories, a subsector of these is governed by a vertex operator algebra. These end up being relatively well understood objects from the mathematical side, but the physics still has valuable input to give to the mathematicians, and we sort of end up with some very cool conjectures for mathematicians, which may not seem so obvious to them. And the other motivation is that these have sort of very deep connections to irregular Hitchin systems, which again are not super well understood, and the geometry Langlands program. So sort of physical input into these problems is always an important thing, and so very could be interesting to the right people. So what will this talk be about? As you can see, there are many ways of constructing Argyres-Douglas theories, and with it comes the baggage of a redundancy in description. And so what I mean by that is many times you have the same SCFT and you're constructing it using different methods. This gets really bad if you just consider the classes type construction of these theories. You see that many different descriptions give rise to the same SCFT. And so you end up having many different names for the same simple physical theory. And this is sort of not nice. You want to be able to characterize a theory sort of cleanly and say, like, have a map of dualities in some sense, so that you sort of restrict the landscape of things that you want to consider, which is what I'll talk about. And so the rough plan will be, I'll first talk about Argyres-Douglas theories and the Hitchin system construction as compactifications of 60 theories. I will talk about some relevant properties for this talk. And then the main results are split in 3 parts. One is there's a particular type of theory which I will introduce, called as type 1 Argyres-Douglas theories, and we'll look at some equivalences between them. There'll be some discussion on generalized gauging description, which will make more sense when we get there. And then finally, I will sort of bring it all together to sort of restrict the landscape and have, like, hopefully a clear, rememberable punchline at the end of the talk. So let me start with talking about what Argyres-Douglas theories are, sort of how to construct them this way. And the starting point is the 62,0 theory. As is well known, these are labeled by an ADE type Lie algebra. I want to restrict my attention to the theory constructed as world volume of a stack of n M5 branes. So the A type 62,0 theory, where the n labels the SUN. Again, this is well known that if you compactify this on a Riemann surface with the appropriate partial topological twist to preserve half the supersymmetry, you end up with some 4D equal to 2 SCFT in the IR of, so taking the volume of this to 0 Riemann surface. More sort of a lot can be learned about this 4D equal to SCFT by considering what I call sort of the diamond of compactifications, where the Argyres-Douglas theory, which we will be constructing, or more generally, this is also true for theories of classes. The 4D equal to 2 SCFT is the one you obtain by compactifying the 6D theory on the Riemann surface. A bunch of information can be learned about Argyres-Douglas theory by further compactifying it on a circle to obtain a 3D equal to 4 SCFT, the name for which I will use the name 3D reduction to mean the direct reduction, the S1 reduction of my Argyres-Douglas theory. But a lot more can be learned about my original Argyres-Douglas theory by reversing the order of compactification. So starting from 60 and first compactifying it on a circle to get a 5D equal to 2 superangles, and then further compactifying that superangles on the Riemann surface with a similar partial topological twist to obtain the same 3D equal to 4 SCFT. Why is this more illuminating? Because, well, you have more control on superangles. It's sort of a Lagrangian theory. You can write down things explicitly and sort of see how your compactification, what the BPS conditions look like. And in particular, the BPS equations for this compactification, which is the same as this, end up are like sort of a set of partial differential equations for the fields involved in the 5D equal to 2 superangles, and they take the form of this sort of mathematically well-known Hitchin system of partial differential equations, which is what I'll very quickly review, because again, this deserves a whole talk on its own. But the basic point is I've written some technical details here for the people who are interested. But let me sort of try to explain this slide in physics terms. This is the partial differential equation that is your BPS equation for a compactification of your 5D superangles, where the A is the gauge field of your superangles, and phi is a particular inner combination of the scalars that appear in the 5D superangles. And so this is just taking the form of a BPS equation, and it turns out to be the Hitchin system of partial differential equations. And there's a particular word for the solution, the space of solutions up to gauge transformations of these equations, called as the Hitchin moduli space. And sort of what you should keep in your mind is that the Hitchin moduli space knows about the Coulomb branch of your 4D theory that sort of sat on the left-hand side of the diamond. It knows more, but sort of this information is sort of very readily available. So, okay, now we want to solve this BPS equation sort of in some generality. And the interesting stuff happens when you allow for some boundary conditions for this set of PDE. And again, in physics terms, you should think of these boundary conditions as some defect M5 branes that are wrapping the four space-time dimensions which the Argyres-Douglas theory lives on, and are intersecting the sort of Riemann surface at a single point. So you have a boundary condition at those intersection points. Now, so let's talk a little bit about what these boundary conditions are. So first, I talk about what could be the familiar boundary condition called as the regular puncture. This is what appears whenever you hear people talk about theories of class S. This is a boundary condition where your gauge field is sort of regular, non-holomorphic, sort of not the non-interesting bit, and your Higgs field phi takes a simple pole at the point where you have the boundary condition, such that the residue of this simple pole is a nilpotent element of your complexified Lie algebra. So in this case, SLN for this talk. Now it's a well-known fact that nilpotent elements of SLN are labeled by integer partitions of n, or equivalently Young tableau with n boxes, which you should think of as specifying the Jordan block structure of a nilpotent element, which you can then compute into an SL2 triplet, and then sort of that gives you the full nilpotent element. And so I will, for this entire talk, whenever you see a capital Y, that is labeling some integer partition of capital N. And the transpose here corresponds to, at the level of Young tableau, literally just transposing. But sort of as a more formal operation, it's called this Waltenstein dual, which for SLN just ends up being transposing the Young tableau literally. And so the upshot of this slide is that regular punctures correspond to a simple pole boundary condition for the Higgs field, where the residue is a nilpotent element, which is a transpose of Y, which labels the regular puncture, which is some notation being annoying that one is Y, other is transpose Y. But that's a regular puncture. That's the more familiar object from theories of classes. The interesting one, which eventually leads to fractional Coulomb scaling dimensions, is the irregular singularity, where now from the Hitchin system point of view, you simply just ask, why should I only consider simple poles? Why should I not consider higher order poles with maybe branch cuts on a Riemann surface and so on? And you can do that. And the particular boundary condition which I will consider is sort of motivated by this series of work by sort of Danchi and his collaborators, where they show that, okay, this particular set of boundary conditions give rise to a sensible SCFT. But sort of before going to the SCFT step, let me just describe what this boundary condition is. There's a lot of information on this slide, so let me sort of take you through what's going on here. There are three things that matter here, which are three simple parameters. It's small n, small k, and small m. So focusing on the top expression here, n and k are just two numbers that is just determining what the higher order pole is here. UK now are semi-simple elements of your GC. So in this case, SLN. And each of these UKs have a block diagonal structure where each block itself is diagonal, but its form is fixed in terms of a set of roots of unity in a particular order. And these A1, AIKs are just unfixed numerical coefficients that are allowed to vary sort of in a physical setup. And the important thing here is that these numbers K and N are co-prime, which is again a condition you take because you can sort of show that the cases where it's not co-prime sort of always collapses to the case where they are co-prime. These are some technical detail. But again, the upshot of this slide is your irregular singularity has been labeled by three numbers, N, K, and M. M tells you the number of blocks you have, N tells you the size of these individual blocks, and K tells you what the order of the pole is. So these three things are describing the irregular singularity. You might ask, what about ULs? I'd never said anything about ULs. The statement there is that self-consistency fixes the exact form of these ULs given what I've written on this slide. By self-consistency, all I mean is that phi is, as I mentioned earlier, is the linear combination of two scalars that appear in the 5 super Yang mill. So this, we want it to be single valued based on physics. And they're clear branch cuts, in this case at y equal to 0. And so you demand that under a monodromy, the overall Higgs field does not change. And this constraint fixes the form of UL to still be diagonal, still be the same block diagonal with the same block structure, different coefficients, numerical coefficients, and the sigma in matrix looks different, but it's still fixed in terms of some rules of unity. And so irregular singularity, as you should believe me when I say this, is labeled by 3 integers, in this case, m, n, and k. And n and k here are importantly coprime. But instead of keeping track of 3 variables, there is a way to reduce it to just keeping track of 2 variables, which are defined p and b, such that the third variable dependence is absorbed in the greatest common denominator of these 2 variables, which is just some relabeling I'm doing so that I'm not in the introducing another new notation for Argyres-Douglas theories, which has been a problem in the past. I should mention here that you can consider more arbitrary irregular singularities from sort of just a mathematical Hitchin system analysis point of view. It is their work by Dan and his collaborators that not all of these correspond to SCFTs, and there's some sort of constraints on what you are allowed to do with the irregular singularity, so that at the end you still get a full SCFT in 4D. And the restriction I will consider here is slightly stronger than what is the most generally allowed thing that you can do. Which is basically, I will consider these numerical coefficients A's to be all generic. So I'm not setting any of them to be equal to each other. So there's no degeneracy generically in my A's. Introducing some degeneracy can sometimes still give rise to SCFTs, though the constraint there is a bit feared. And so I won't consider those cases right now. So it's still a pretty generic set of things I'm considering here. The question is, okay, not everything gives rise to an SCFT. What is the exact setup that gives rise to an SCFT? And there's a sort of a set of arguments, which I'm not presenting here, but I'm happy to talk about eventually, is that the setup that gives rise to Argyres-Douglas theory is that you want to consider Riemann surface to be a CP1, such that you have put one irregular singularity at one of the poles and at most a regular puncture on the other end. So this is related to basically a Riemann surface should have a C star, a sort of a well-defined C star action on it, or this U1 action, which sort of ends up being a part of a superconformal algebra. And so you're not allowed to consider more general Riemann surfaces or CP1 with more punctures. You're restricted to one irregular, and one regular puncture. And so I introduce the notation, this DPB, SLN, Y, where SLN is telling you that we're considering SLN Hitchin systems. P and B are the 2 variables labeling the irregular singularity. And so you can sort of construct the entire exact behavior of your field phi at the irregular singularity by just knowing P and B. And Y is labeling the regular puncture partition. And so it's again telling the transpose of this Y's nilpotent element is the residue of the simple pole of the regular puncture. Upshot being, this sort of defines you the full Hitchin system data you need to specify an Argyres-Douglas theory. And the reason for this is for the people in the know, this is written in a way so that it generalizes the common geometric engineering notation for Argyres-Douglas theory, which is this DPB, and it sort of just extends that sort of. Now let me introduce the so-called star of the talk, which are these type 1 Argyres-Douglas theories, which correspond to the special case where the irregular singularity, one of the parameters in the irregular singularity is set to n, for SLN again. Why is this special? It's special because we have extraordinary control over what's going on in these theories, because for these type 1 theories, so B equal to n and P being generic, but the regular puncture being the partition being 1 to the n or n, you can also construct these theories by the geometric engineering picture. And these 2 pictures give you access to not the same data. You can learn independent things about the same theory by constructing it in 2 different ways. And this is useful because then for type 1 theories, you can actually sort of amass a decent amount of information about sort of the physics. And so I will adopt a special notation for type 1 theories where I hopefully simplify the notation by not writing a B every time it's type 1, because it's exactly this number SLN that appears here. So whenever you don't see a number in the superscript of a DP SLNY. Just remember that it's the same number that appears in the SLN up there. So I will now go on to talking about properties of these theories, but I think it's a good time to stop here and ask if there are any questions. All right. Moving on to the properties. The first property should be the defining one, is that the Coulomb-Run spectrum has scaling dimensions that are rational numbers. But now that we have explicitly constructed explicitly characterize these theories as compactifications of 6, 0, 0 theories, these are rational numbers with the denominator n plus k, or p over m, or q, which are all the same thing because there are a few parameters and I'm just keeping track of the relation between them. The flavor symmetry of these theories has a contribution from the regular puncture and from the irregular singularity. The irregular singularity contributes a bunch of u1s and a non-abelian factor, which is n minus b. Whereas the regular puncture has the usual class S contribution, which is sort of spelled out here. So for a given partition, this is a thing you can write down immediately. And sort of while I have this on the slide, I made a comment about sort of the partition 1 to then being referred to as maximal / full puncture, and the partition n being the no puncture case. Sort of see the reason for that here is that when you take y to be 1 to the n, so all these ln to L2 are 0, the flavor symmetry you get from this is exactly SUN, which is the maximum amount of flavor symmetry you can have from a single regular puncture. Whereas when you take this partition to be capital N, so L capital N is 1 and everything else is 0, then you get no flavor symmetry. So it's sort of equivalent to having no regular puncture. So the term maximal regular puncture or maximal puncture or full puncture refers to the partition being 1 to the n, which is a terminology I'll use. So maybe that's useful to keep in mind. And then sort of the more interesting data here's where Quiver start coming in, is that you can look at 3D direct reduction of type 1 theories. Let me describe it. Again, just to recall, these are the direct circle compactifications of Argyres-Douglas theories. It turns out for type 1 theories, these admit we immediately know a direct Lagrangian description for these 3D n equal to 4 SCFTs. And it's rather simple because when Pn and are co-prime, again, it's type 1, so B is equal to n. So this is labeling the irregular singularity, co-prime P and n. Up to free twisted hypermultiplets, these are just T rho sigma theories, which are, again, we understand them, we like them with this particular partitions, which is, again, I've just put in the details for people who really care, but the details are not so important at this point. And when P and n are non-co-prime, it's no longer T rho sigma theories, but they are still linear USQ quivers. So still pretty understandable. And there's a curious fact, which we'll come back to, is that the number of special unitary nodes in this quiver is exactly the same as the number of n equal to 2 exactly marginal deformations in your Argyres-Douglas theory. So there's a 1-to-1 map there between the SU nodes that appear and the exactly marginal deformations that appear, which will, again, just keep that in mind because that will come back in a bit. So this is a 3D direct reduction, but I'm talking about type 1 theories. Well, it turns out the 3D mirrors of these quivers, or just in any case, the 3D mirror of Argyres-Douglas theory compactified in a circle, are Lagrangian generically, and we exactly know what this Lagrangian looks like. And it takes the form of a quiver that has a complete graph of U1s and 2 tails that extend from it. And the 2 tails, one way to think of them is that they carry the 2 non-abelian flavor symmetry. One, the SUN that comes from the regular puncture, and the SUN minus B or NM that comes from the irregular singularity. And the U1s that came from the irregular singularity are there in the complete graph. So again, I've drawn it only here for the full puncture, but sort of this is just a TSUN tail. And so reducing this puncture just gives you another T to sigma tail. So this should be pretty understandable. But yeah, upshot here is again that the 3D mirrors of all these theories are unitary Lagrangian, sort of unitary quivers. And they're not linear, but they're unitary, whereas the 3D reductions are linear, even if they're not necessarily unitary, they're especially unitary. Finally, before sort of going into the results, there is an important RG flow that interpolates between many of these Argyres-Douglas theories, which is via this process called as nilpotent Hitching. And the way you should understand this is that if I start with a theory labeled by the irregular puncture P and B of some SLN Hitchin system, if I start with the full maximal puncture, again, recall this has the SUN flavor symmetry, then the Higgs branch of this theory has an SUN flavor symmetry acting on it. And there is a moment map operator that lives in the adjoint of this SUN, which you can give a non-zero wave to. Now, since this lives in the adjoint, this non-zero wave is proportional to some element of SLN, which I take to be some nilpotent labeled by some partition Y. The statement here is that when you give this wave, this introduces a scale. So then you sort of flow to the II where the scale vanishes and you end up hit an SCFT. The SCFT you hit is the one that is labeled by the same P and B, labeling the irregular singularity as the original one, but the regular puncture has now a different partition labeling it. So this tells you how to change the regular puncture starting from 1 to the n to anything without affecting the irregular singularity at all. This is, again, a familiar thing from just theories of classes, which sort of also is true here because it's the same operation. And the reason it's called is partially closing the puncture is because now if you look at the flavor symmetry corresponding to this more generic partition Y, this is now a subalgebra of the larger SUN subalgebra that you SUN algebra that you started with. So sort of the size of the puncture is correlated to how big the flavor symmetry is, and then reducing it sort of closes the puncture is what the idea is. But this is sort of the end of my review part, so to speak, and now I will move on to the actual results. In particular, I will first talk about type 1 Argyres-Douglas theories and discuss 2 equivalences that should be interesting. Okay. So the first equivalence is that there is one SCFT I'm talking about. Okay, no, let me say this way. These two distinct descriptions, which are distinct because you can see that just the SLN group labeling the Hitchin system are different here. Here L is any positive integer. The regular puncture is different, but these two are describing the exact same SCFT. And so this is sort of exhibiting sort of an infinite redundancy in this description of this one SCFT labeled by the left-hand side. You should immediately ask if you sort of are familiar with if you remember how the flavor symmetry from the regular puncture works, is that there seems to be an extra SUL flavor symmetry that's sitting here. The statement is that if you calculate its flavor central charge or the anomaly, you see that this vanishes. And so effectively this flavor symmetry is decoupling and not playing any role in the actual physics. And so that's sort of like the baby check that this actually holds true. Obviously we did more, but before going there, let me just sort of rephrase this sort of as a more practical, usable statement, where if you are ever in a situation where looking at a type 1 Argyres-Douglas theory that looks like the bottom thing, where you have some D7, SL34, and some generically horrible looking partition, but you have a bunch of 7s appearing, this statement is telling you that you can ignore those 7s and sort of change the irregular singularity numbers here such that this SL becomes 13 after removing this. And you are still describing the exact same as SCFT. So this number of 7s appearing here is completely redundant and you don't need it. In diagrams, all it means is that if you have columns of length P, all of them can be removed and you just need to focus on the white part here. And so practically this is sort of useful. Again, what kind of concrete checks we did, the main check that we have done for this is that the 3D reductions on the two sides computed independently match exactly. And this match is done by doing some cool stuff. Pretty basic, very cool stuff. And so on this slide, I've presented sort of this equivalence highlighted in the box where I have some D3SL4 of sort of the full puncture and D3SL10 of a partially reduced puncture. The way to check many of these dualities, at least the way we have done it, is to consider this theory on the right-hand side as living on the Higgs branch of the top theory, where the puncture is full, so it exhibits the full SU10 flavor symmetry. And then giving this SU10 flavor symmetry a wave to obtain this theory. Why is this useful? Is because it's sort of much easier to write down directly the 3D reduction of the top guy, which just ends up being this theory, which is a T rho sigma theory with particular rho and sigma. And this is again a linear unitary quiver. So we are very happy to be able to write a Hahn-Newton brane setup that describes it. Just to mention it once, the vertical lines here are NS5 branes. The orthogonal ones are orthogonal blue ones are D5 branes, and there's the black D3 horizontal brane that stretches between them, and the numbers label how many D3 branes are stretching between them. And again, this setup gives rise to this quiver here. Why is this useful? Again, nilpotent Higgsing in this case, or changing this 1 to the 10 to 3 square 1 4, is just taking a bunch of these D3s stretching between some D5s and then lifting them up and sort of decoupling them by throwing them to infinity. And again, the process, which ones you do that to is determined by what nilpotent wave you're giving. And in this case, implementing this nilpotent wave gives rise to this Hahn-Newton brane setup. And now you can do the cool part of this, where you can do the Hahn-Newton, basic Hahn-Newton moves, where you want to take these two D5 branes here and then move them all the way to the right-hand side. Hahn-Newton moves will basically tell you that whenever you move a D5 through an NS5, there's going to be an annihilation or creation of a corresponding D3 brane that stretches between them. And upon doing that, the number of D3 branes stretching between various D5 and NS5 changes in the following way, and you end up with two decoupled D5 branes. They're decoupled in the sense that the world volume theory living on this 3 equal to 4 theory living on this world volume of these D3 branes stretching do not talk to the decoupled D5 brane, so we can ignore them. And the quiver that's describing this setup here is this one, which is again a T rho sigma of SU4 theory, which you can independently check is the 3D reduction of the left-hand side. And so by doing some gymnastics, we sort of show that the 3D reduction of the two sides exactly match. The curious fact here is that if you notice, the number that's redundant here is 3 because this is a 3, but there are 2 3s that we are removing, which exactly is the number of decoupled D5 branes that we have. And so this exercise can be repeated in a fair amount, in complete generality, where in this expression, you will have L number of D5 branes, decoupled D5 branes that become decoupled when you sort of pull them to the right-hand side. And so again, you can check this very generally as we do. But this is the first equivalence. The second equivalence looks different. Again, there's some technical details here if you're interested, but let's look at the example because it's very visual to see what's exactly happening here. And the idea is you start with some theory labeled by 7 and 13. That's the irregular singularity, and the regular puncture labeled by this generic partition, which is denoted in white here. And you put it in a rectangle that is of height p. This automatically defines a complementary partition, sort of represented here in red for you, that sort of sits inside this box. And the statement is that I can now take that to be the regular puncture associated to some setup with a corresponding irregular singularity where this number 7 has to match because that tells you the denominator of your Coulomb branch spectrum. Then these two things are describing the same SCFT once again. So this is again a redundant description of the same SCFT. And again, explicitly writing it down in terms of full generic partition, it looks like what I've written on the top. But the idea is in any example, just like do the rectangle thing and flip it, and it's sort of pretty clear what you're doing. And how do you, and what does the check for this look like? Once again, we check all the discrete data and everything, those things match, but the real check is a 3D reduction. And 3D reduction also sort of, you can see matches where the idea is very similar. again, I've represented this example sort of worked out here. Once again, you think of the right-hand side as living on the Higgs branch of this top theory with the manifest SU12 flavor symmetry on the Higgs branch. That has this particular quiver, this particular Hananivitan brain setup, the nilpotent Higgsing. You move these D3s stretching between D5s to infinity to end up with something that looks like this. And then I take all of these 3 D5 brains and do a sequence of Hananivitan moves to move them to the right-hand side. And doing that changes things. In particular, it gives you a bunch of decoupled NS5 brains. And again, these are decoupled because I'm not talking to the D3 world volume theory, which is what the 3D equal to 4 SCFT is, which in this case it is a TSU3 theory, which is exactly a 3D reduction of the left-hand side. And so again, even this you can do very generally. In the previous case, you were only moving L number of D5 brains from the left to the right. Here you move all of the D5 brains from the left to the right, and you get a match between the 3D reductions on the two sides. So this is sort of the main two families of equivalences between type 1 Argyres-Douglas theories. And now I will move on to the second set of results, which is this generalized gauging description. But let me first set up some intuition for what I mean by generalized gauging description. And the intuition comes from theories of classes. Once again, to just reiterate, theories of classes correspond to the compactifications of CC2, 0, now on a generic Riemann, genus G Riemann surface with an arbitrary number of marked points, modulo some simple exceptions. These are, again, very well studied. You might probably have heard about them many times before. But the property that I want to focus on here is that the n equal to 2 exactly marginal couplings of your 4D SCFT theories of classes are in one-to-one correspondence with the complex structure moduli of this Riemann surface, genus G, S mark points. And the idea here ends up being that certain degeneration limits of these complex structure moduli of this Riemann surface correspond to taking the gauge coupling, taking some parameter that you should think of as the gauge coupling to certain limiting values because of the one-to-one correspondence. And in essence, the pair of pans decomposition of your Riemann surface ends up being like a gauging description of a 4D SCFT, where each pair of pans or 3 punctured sphere corresponds to a particular SCFT. And you should think of the pair of pans decomposition as taking your Trinian SCFT corresponding to 3 punctured spheres and like gluing them together using some vector multiplets to form the full theory. A simple example to keep in mind is the case with the theory of classes corresponding to the SU2 C0, 0 theory, which is sphere with 4 punctures. This is a simple gauge theory, SU2 with 4 flavors gauge theory. And you can think of the 4 punctured sphere as you can sort of degenerate it into 2 3-punctured spheres as sort of joined together. And each of these 3 punctured sphere then corresponds to a bunch of free hypers. And you can sort of see gauging together a diagonal SU2 of this bunch of free hypers gives you the SU2 with 4 flavors, which is exactly reflected in the fact that a sphere with 4 puncture can be degenerated into 2 3-punctured spheres joined together by a tube. Here in the theories of classes, there's this very nice geometric interpretation. But the thing I want to take forward from this is that there is an idea of whenever there's an exactly marginal deformations, I'm able to write it down as gauging of 2 Trinian theories or a building block, which in this case ends up being the theory corresponding to 3-punctured sphere. While the geometric intuition here does not sort of follow through to Argyres-Douglas world, the result sort of does. And I sort of demonstrated first with the help of an example where I've considered what I consider to be a pretty horrible theory. Well, to look at. There's irregular singularities, some 9 and 30, and there is this weird partition which I cooked up for demonstration. In particular, the important feature of this theory, the reason I've chosen it, is that it has 2 exactly marginal deformations. And so recall from my review section, I said exactly marginal deformations are in one-to-one correspondent with the SU gauge nodes that appear in the 3D reduction. I've run the 3D reduction of this guy here, and you can see there are two SU gauge nodes here. And following from the class S intuition here, sort of seeing it in action here ends up being that you have three Argyres-Douglas theories themselves, which I've noted in color, that do not have any exactly marginal deformations. And if you gauge them together by sort of using SU gauging, and there's some extra charged hypers under it, you see that you're able to reconstruct the exact data of the theory on the top. Said slightly differently, or maybe the same way, the top theory can be thought of as gauging together, sort of linearly gauging together three Argyres-Douglas theories that do not have exactly marginal deformations. And while I've only been as an example, this ends up being the full statement where the trinions in the world of theories of class S get replaced by these co-prime type of Argyres-Douglas theories, where the co-primality is a sufficient condition for not having any exactly marginal deformations. Now I will probably display the worst slide I have on this because it's extremely technical, but let me walk you through what's going on here. You just need to listen to my words, not sort of really stress about what's here. The reason it looks technical is because it's completely general. It's extremely explicit. And so you can just plug in whatever you want and get the answer you need. But it's a very simple thing happening here. On the left-hand side here, we are starting with some theory that generically has exactly marginal deformations. And we're saying that I can think of this equivalently as taking these two theories. Again, there's some labeling, there's some irregular singularity, there's some regular puncture, but I gauge them together using some SU gauge node. And I'm telling you in this formula exactly what the rank of this gauge node is and sort of what part of flavor symmetry you're gauging in the regular puncture. Again, the next important part is that this theory on the top has no exactly marginal deformations. So that's good. The theory at the bottom generically has exactly marginal deformation, but then it's of the form, it's sort of, you can reapply this formula to the bottom theory. And then you get, again, like this, the bottom theory has two theories where the first one won't have exact marginal deformation and the second one may have. And then you sort of do it again and just keep doing it recursively till you end up with a linear chain of theories that do not have an exactly marginal deformation, and they gauge together by some SU gauge node, which again, if you sort of follow the formula, it's sort of pretty simple to see what the formula is, and you can explicitly write it down, like we did in this example particular. For some people who are, an observation that you can see here is that if you take y to be 1 to the n, which is maybe arguably the simplest partition, you can take the entire flavor symmetry on the right-hand side gets sort of is manifest in the first theory here itself, because this y tilde plus corresponds to q minus 1 to the n here, if this L1 was equal to capital N, and obtaining this theory with generic y can again be thought of as nilpotent Higgsing the one corresponding to 1 to the capital N. But on the right-hand side, you have gauged a part of this theory, and they're going to be non-trivial Higgs-Brunskiral ring relations, which will force you to turn on Wef for some operators charged in this gauge symmetry. If you turn on the Wef for the SU and flavor symmetry. So it's one reason to understand why this expression was complicated is because it exactly characterizes what the propagation of giving you just a SU and flavor symmetry some Wef is going to be on your entire gauging description. But again, it completely captures that.
Could I ask, I'm missing here.
Yes.
How do you determine Q in this?
Oh, Q is P divided by GCD of P and N.
I see. And little m is that GCD?
Little m is that GCD, yes.
Thank you.
Okay, thank you very much. Yeah. So yeah, that's this expression. Again, this is more of, okay, this can be done. And this slide is, you're supposed to just take away from this that, okay, if you're really interested in this, you can go look at the paper and there is an explicit expression where you can plug in numbers and get the answer you want. The more philosophical statement here is what I already said. Whenever you have an exactly marginal deformation in Argyres-Douglas theory in this class, you can think of it as linear gaugings, linear gaugings of a bunch of Argyres-Douglas theories that do not have any exactly marginal deformations. So in some sense, the ones that do not have any exactly marginal deformations already determine the ones that do, which is sort of the punchline. Now, if you have been following this talk, you must have a complaint that I sort of set up a very generic set of Argyres-Douglas theories. I had this parameter B that I just set equal to n in the beginning and then just talked about type 1 theories. I didn't talk about anything else. You're wondering why was that? The reason is that all of those theories can be equivalently described as some type 1 theory. This is, again, the sense in which type 1 theories are really the special things in this class of theories. And just sort of, you can see the expression on the left-hand side here, I have a generic theory. So this P and B, importantly, B is generic. It's not equal to N, some generic puncture. And the statement here is that this here on the right-hand side, which is a type 1 theory, I've expressed that by not writing the superscript here. Up to this free sector, exactly describes the SCFT on the left-hand side. In particular, again, for people who know something about this, this means that all type 2 theories are also just type 1 theories. You don't need to talk about type 2 theories again in this context. And this is cool because it significantly restricts the number of things you need to talk about. And as I've already hopefully communicated, we know a lot about type 1 theories. So this essentially just increases the amount of knowledge we have about Argyres-Douglas theories by a fair amount. How do we know that this is true? Again, I will demonstrate it by an example, which is this D4 to SL4, 1 to the 4. So this is not a type 1 or type 2 theory. This type 1, this number is 2, not 4 here. And the statement here is that this SCFT is the same one as described by this type 1 theory, just some SL10 Hitchin system with P equal to 4 and this 3 square 1 4 partition. The way we check this is obviously apart from discrete checks, which there's no point in displaying in our presentation. We do the 3D mirrors now, not the 3D reduction. Recall the 3D mirrors took the form of a complete graph with 2 tails that stretch out. And here, once again, I've taken the point of view where the theory on the right-hand side lives on the Higgs branch of the theory with the same irregular singularity, but the full maximal with the maximal regular puncture correspond to the SU10 flavor symmetry. And the 3D mirror of that guy looks like this. Again, you can see the complete graph here, and there's a small tail here and a long tail here. But you can check that all these nodes here are balanced, and there are 9 of them. So this forms an SU10. There's an SU10 flavor symmetry that you can read off from here. And this nilpotent wave on the 4D theory correspond to some 3D Coulomb branch wave, again, because we're working on the mirror side. And we want to find out what this question mark is. The statement will be that this question mark will exactly end up being the 3D mirror of the theory on the left-hand side, which people have conjectured independently. And so the way we do this is by some gymnastics. So let me again walk you through this. You start at the top left, which is the 3D mirror corresponding to this D4 SL10 1 to the 10. So this has a full SU10 flavor symmetry, again manifest in this tail. Notice that there is no framing in this quiver. And so there is an overall U1 you're allowed to decouple. We choose that to be one of the ones in the complete graph. And then the other one that's remaining, we ungauge it by gauging the U1 topological, the complete graph to sort of obtain one free hyper that's charged under it, and just 2 frames now. The bottom part does not get affected by this. And this now is a linear unitary quiver. And so this is a T rho sigma theory. And you can write down exactly what T rho sigma theory it is, sort of pretty simply. It's this one. And now the 3D Coulomb branch wave that we wanted to perform, which was this 1 to the 10 goes to 3 square 1 4. In this language, is just like changing this number to 3 square 1 4, which you should recall. Technically, you should like write down or you can write down the Hannah-Newton brain setup for this, and then take a bunch of D3s, and then let's now in between NS5s because we're on the mirror side, and then lift them up to perform this wave. The hyper or the flavor nodes here do not get affected by this operation, because this again happening on the Coulomb branch of this 3D theory, where these objects living on the Higgs branch of this 3D theory. And so once we have done this Coulomb branch wave, we can undo what we did on the top line by gauging the hyper together with these two flavors here in the exact same way to form a complete graph. And the thing you end up at, as I promised, is the 3D mirror of this non-type 1 theory that we started on the left with, which you can get independently. While this is sort of somewhat explicit, it is much easier to just go from top left to bottom left directly by this method of inverted quiver subtraction, where you would do like a subtraction by a non-elementary slice here, which I've written, slice quiver here, which I've written down here, which in this language from sort of going to right, down, and left corresponds to the D3 brains that says between NS5s that are going to lift to infinity. It follows exactly this pattern. And so this determines the quiver that you need to subtract to perform this 3D Coulomb branch wave on this guy directly. So in an example, this is sort of how it works, but this should sort of convince you that this can be done quite generally, because the thing we want to do is sort of look at this bottom line and verify that this is true on the 3D mirror side. So the 3D mirror of the left-hand side, you can write independently and keep it on the side. Then you can try to think of a 3D mirror of the theory on the right. Then first realize that this should be on the Higgs branch of the theory on the top with the manifest SC flavor symmetry. And then this wave corresponds to subtracting a particular quiver from this quiver tail that the union of two quiver tails that has this manifest symmetry. And this particular partition will let you determine exactly what quiver needs to be subtracted to be able to do this. And when you do that on the generic quiver describing the top guy, you get exactly on the nose the quiver that you expect from the left-hand side. And so this check we have done sort of very, very explicitly, and it sort of just works out. It's very nice. And so the 3D mirrors in this case also match the sort of providing as much evidence as we could provide for the fact that this statement is true. So indeed, you only need to care about type 1 Argyres-Douglas theories when talking about the set of theories that I presented here. Just to summarize quickly, we studied SLN irregular Hitchin systems and Argyres-Douglas theories that come out of it. There was some restriction on the type of irregular singularity we considered, the real restriction being that the numerical coefficients, these AIJs, were not allowed to be generic, were allowed to be generic and not having any degeneracy. We then discussed two large families of equivalences within type 1, sort of expressing that, okay, we know a lot about type 1. So, and within type 1 itself, the set of independent objects is reduced. Then we presented a gauging description for type 1 theories, where the co-prime type 1 theories or type 1 theories without any exactly marginal deformations served as a building blocks or like the matter content of this gauging description. And then finally, we conjectured that all Argyres-Douglas theories that we consider have an equivalent type 1 description. So you only need to talk about type 1. And so the punchline, which hopefully should make sense now, is that co-prime type 1 theories are the basic building blocks for this, in that you can gauge them together to form the ones that are non-co-prime, and everything else just collapses to this set. I will thank, okay, make it so sorry. Yeah, just a quick outlook. It has some interesting geometric engineering implications. If you can consider the two theories, in this case, the type 2 theory and type 1 theory, you can construct both of them independently from a geometric engineering description. And then there is an interesting question about what does this equivalence mean at the level of geometric engineering. Then there's the obvious extension to more general G and inclusion of automorphism twists. At a practical level, this means that you no longer end up working with unitary and or USU quivers. Now you have orthosymplectic quivers and especially unitary nodes on top of that. And so the analysis in principle becomes slightly more difficult in that way. And then there is the more elusive extension, which is to this so-called type 3 Argyres-Douglas theories, which is a bad name. But all it means is this degeneracy of these numerical coefficients, which I didn't allow, should now be allowed. The reason it's elusive is that we don't really understand very well which of, like, allowing what degeneracy really gives rise to an SCFT. And so talking about them in the first place is kind of sketchy. But also, we know very little about about these theories. So there is no clear organizational principle for how you should think about what are the families that sort of appear here and how you should think about these. At a practical level, this means working now with quivers that have a complete graph that can now have higher rank gauge node, not just U1s, and 3 tails coming out of them. So that's, from that perspective, it seems not too difficult to do that, but maybe there's something there. But I will stop here and thank you.
All right, let's think, Palash. Do we have questions?
I have a question. Hi. So do you have like a motivation from the Hitchin system point of view for why the singularity of the type 2 puncture and the singularity of the type 1 puncture should be the same?
Unfortunately, no. As far as I understand, these are more predictions for what the Hitchin moduli spaces should look like. From just the perspective of the Hitchin system, I would have not expected this. But it's more of, okay, when you actually start if it's as simple as the moment you compute the spectral curve, you see that, oh wait, I'm seeing the exact same numbers appearing. Is there something more? And then you go and do other checks, but it sort of does not work the other way around, where Hitchin system informs you about this equivalence. Unfortunately, is the answer.
I see. But probably with hindsight, perhaps one can go back and figure it out now that
probably. I mean, I guess the main roadblock there ends up being, from what I understand, we don't really understand irregular Hitchin moduli space. It's a aptly named wild territory. So it's unclear. I think with better understanding, it's possible that we just like see this, because again, the 3D mirrors we're talking about here are natural Nakajima quiver varieties associated to the Hitchin moduli spaces. So there should be a way to sort of just see this from first principle, but I don't know how to do that, or if that can be done at the moment.
Yeah, thanks. I have a related question, which maybe is equally difficult. So you can take the VOA for each of these theories as well, and you can ask, is there now, so a priori those VOAs also look different, right? So is there some isomorphism between VOAs that you're predicting here or something?
Yes, absolutely. Yeah, I didn't present that bit, but yeah, there is a set of equivalence, the set of isomorphism which we are predicting here. Some of them were known. This phenomenon in particular, if I can go here, this phenomenon where you can like ignore a set of length p columns, is this phenomenon called collapsing levels in the VOA literature, where a bunch of sort of at special values of your flavor's central charge, or like the K variable in your VOA, this is affinely algebras, your VOA just shrinks smaller into size. So start with some SL34 affinely algebra, but you end up with SL13 because sort of all the information just shrinks down. So there was some hints of this. The isomorphism predicted by this one, to me, is genuinely new, even from the VOA world. And again,
the name for shrinking the VOA?
It's collapsing levels.
Sorry, can you say it?
Collapsing level.
Collapsing level, okay.
Yeah. But yeah, this one seems to be new, and maybe I should mention, like, again, from VOA is where you can VOA is one way to see exactly what the Higgs branches of these theories are in terms of like nilpotent orbit slices and or their hyperkähler quotients. This again is sort of a prediction for those things. Again, in some examples, these are things that were known before, but this is sort of a more systematic thing that you can now make, where some examples you can go back and justify because we knew it. But overall, it's a prediction.
Yeah. Okay, that's very cool. Thank you.
Thank you.
Do we have more questions?
Most quivers will be complicated quivers with very badly behaved moduli spaces. Can you identify subsets which are nicely behaved?
Yes. So the I'll say this. The co-prime one, the condition where these P and N variables are set to be co-prime, these are these are going to end up just being linear unitary quivers. And so even the moduli spaces are going to look like slices of nilpotent orbits and so on. Once you let go of this co-primality condition, you'll this generalized gauging description is suggesting that you're supposed to take hyperquiller quotients of like two of these nilpotent slices that come from these exact co-prime type 1 theories.
Mhm.
And so you can get some, again, it's not a great answer, but it's like the best I can say at the moment about the moduli spaces of the non-co-prime guys. The co-prime guys are definitely just nilpotent orbit slices. They're Higgs
Well,
slices.
let's ask in a different way. What's your favorite one?
The co-prime ones, yes. The co-primes one with 1 to the n, because I think I have an extra slide for that. Yeah, so when you're just within type 1, when you have the full puncture, you just get closure of a nilpotent orbit. So this is nice. And then closing it, you just start taking slices. So these are pretty well behaved and nice. I like them.
And the orbit is with this partition that you're showing?
Yes, that's the partition leaving the orbit, yeah.
I see. Mm-hmm. Okay.
And then you're somehow supposed to make sense of taking a bunch of them and taking their hyperkiller quotient and then slicing them further. So it gets messy indeed.
I see.
So among these type 1 co-prime, there are still identifications from those
Yes.
first set of things. Is it easy to say what's a, kind of smallest p representatives of each of those equivalence classes, or is it just a complicated number theory?
It's unfortunately a complicated number theory question. Like, we tried to get this, and we had some form of belief that these two equivalences that we have written, when restricted to the cases of co-prime type 1 theories, are all that exist. And we still sort of believe that, but there is we can't prove that that is the case.
Mm-hmm. Okay.
So it's sort of, that's the best I can say at the moment. Because you may always end up, again, this is again still restricting within just type SLN. There are weird isomorphisms between theories you construct from an SLN system and like an SO2N system, and
Sure,
they still get the same theory. So again, it sort of keeps, the redundancy keeps proliferating significantly. So it's really hard to make a sharp statement about sort of this being the minimal set that's independent, and there's no isomorphism between any of these things.
okay, thanks.
So within the type 1 and type 2, do you expect even more isomorphisms, or like how do you see it?
In what sense? I didn't understood the question.
Do you expect that like you found like certain sets of isomorphisms, but do you expect that there will be like many more to explore, or it's more of an opinion question? It's not very precise.
I think if you combine all the ones that we have, so you can start doing funny things now. You can start with the one I've written here, and on the right-hand side, apply a bunch of like the type 1 isomorphisms I discussed, and then say that, oh, all of these are equivalent to type 2, and then start generating new families from there. But again, that's sort of not that interesting. And again, my statement sort of in the same vein as what I said to Philip would be like, the set of equivalences which I've presented here is what I want to believe are the things that you will find, apart from maybe some accidental isomorphisms here and there. But I can't show that is indeed the case. It's what I believe.
Do we have more questions? Yeah, if not, then I would say let's thank Palash a final time. And we can go off the record.